Hello dear students, I am Samir Velankar. I welcome all of you to this video which is based on the topic binary search algorithm. In the previous video, we saw how binary search works with some examples where the value was either found or not found, and we saw how left, right and mid, the three counters, help binary search find out whether a value is present or absent. Now in this video, we will find out how do you write binary search algorithm. There are two ways obviously of our writing binary search algorithm. We are going to learn non-recursive method in this video. Recursive method will be seen in the next video. I have kept myself ready with an array here, and note that this array is sorted in increasing order, and let's find out how the algorithm runs on this array. By the way, when we run an algorithm on paper, just produce the diagrams that we were drawing in the earlier video. The values of left, right, and mid, how they varied, and how we saw the process of binary search. The same thing has been written in the algorithm. It's only written in English. That's all. Otherwise, you should see the diagrams that we were seeing in the earlier video while watching this algorithm. Okay, let's see. Binary search algorithm will receive an array. Of course, the array is sorted and it will receive the size of the array. N is the size of the array, so the elements are 0 to n minus 1. And it will receive, binary search algorithm will receive the key which we want to search. Let this key be equal to x. Now to search x, you recall that we used one counter called left, which began with left end, that is 0. We also used a counter called right, which started with n minus 1. So n minus 1 in this case is 5. And for this left and right, we found out the midpoint. The midpoint here would be 0 plus 5 upon 2, that is 5 upon 2, that will be 2. This is mid. Mid is 2. Now for some time, you imagine that this key, this is x, the key is 10. That means user has selected this key to be searched. Is x, that is 10, present or not in the array is the question. Now we have done the three initializations. Left is 0, right is n minus 1, and mid is 2. Now watch, the while loop will take all over the control. The while loop is going to control the process of binary search. And the while will continue as long as a of mid is not equal to x. Now notice this is one of the features of the search algorithms. Whenever we write any search algorithms, then not equal to is our favorite operator. Because why I am telling you all this is because it is so obvious that when we search for something, we search that value till it is not found. But when the value is found, we stop. That means the while loop, the ideal condition in the while loop is supposed to be while a of mid is not equal to x. Now just check what is a of mid. A of mid means a of 2, which is 10. And what is our key? X is also 10. We are looking for 10, and 10 not equal to 10 is false. We have got the value, isn't it? So this while loop will break straight away. It's not going to execute at all because the condition in the while is initially false. Isn't it so? Well, I will suggest all of you to ignore that left less than or equal to right condition for some time. But intelligent readers would have known it already, because this is another case where the binary search can terminate when left crosses right. But for some time, you ignore that condition. Okay, so the while has stopped because a of mid here was 10 and the key we were searching was 10. So 10 not equal to 10 is false. So the loop has stopped. Now what? Now once we are out of the loop, once the binary search has gone out of the loop, we now check why did the loop stop. We now check the status of the loop. We ask, has the loop stopped because left has become greater than right due to this condition? Now you watch that this condition is still false when the loop stops. This condition is false because left is still 0. Observe, left is still 0 and right is still 5. So left is less than right. So the condition is false, and if the condition is false, we will go to else and we will return mid. What we are returning is the position at which the key was found, and genuinely the key was found at second position. We call it as success because the key was found. So this was the first execution of the binary search. I thought that we should execute the binary search with the value found immediately at mid, isn't it? So that we would know that what happens very first time when a of mid becomes equal to x, the loop stops. Let's take another example now. Let's run through this binary search algorithm with key equal to, let's say the key is 8 now. Instead of 10, the key x that we are searching is 8. So how is this going to run? Obviously left is 0, right is 5 in our example, and midpoint calculated is 2 again. Now watch, a mid means a2 because mid is 2 and that is 10. A2 is 10. Is it not equal to the value that we are searching? Now the value we are searching x is 8, and indeed the value at midpoint, that is 10, is not our value that we are searching for. So the condition is true. Of course, left less than right, the first condition is true because 0 is less than or equal to 5. So as both the conditions are true in the while will operate. And now the decision has to be made. Okay, the decision is that we know that value was absent at midpoint, isn't it? So where can this value be? We are searching for 8. And if the value is absent at mid, it can be either to the left of mid or right of mid. That depends on this condition. We are going to now check if a of mid, notice a of mid is 10, is it less than value at midpoint, is it less than the value that we are searching for, 8? That's false. So obviously the value at mid is such a value which is greater than the key that we are searching. So the key is less. So it must be to the left of mid. Hence we jump to else and we make right equal to mid minus 1. What that means is now right, which was all the time 5, is going to change to 1. Isn't it so? So we are now looking for 8, the key that we are searching only in the region left to right. Observe, left is 0 and right is 1 now. What next we do? Now we have executed else part. The next and the most important thing is we will have to recalculate the midpoint because right has changed. So the recalculation of the midpoint will be done by adding left, that is 0, with right, that is 1, and dividing it by 2. This is 1 upon 2. Just don't get mistaken. 1 upon 2 is 0. Hello, 1 upon 2 is 0. So the new mid calculated is 0. So I'll update the diagram. The new midpoint calculated over here is 0. So left and mid are at the same place. Okay. Now let's go back to while loop and recheck the condition. The condition holds true again. Observe the while. The first condition holds true because left is less than or equal to right. Because 0 is less than or equal to right is 1 now. And a of mid, observe a of mid is 5 because a of mid means a of 0, that's 5. Is it not equal to the value that we are searching? Yes, the condition still holds true. That means midpoint is not storing the value in which we are interested in. So we should continue. But then we will now check, okay, if the value is not at midpoint, then what's the relation? Should the value be to the right or to the left? So we will go with the if again. If a mid is less than x, now notice a mid is 5. Is it less than x? X is 8, which is true. So surely 8 must be to the right of midpoint. Hence we make left equal to mid plus 1. So now here gets the updation done. Left is becoming equal to mid plus 1 means left will now become equal to 1. I hope you are carrying this properly. Left becomes mid plus 1, isn't it? And indeed, you will agree that now we are searching the value 8 from position 1 to position 1 because left and right both are 1. Okay, so now we have updated left. And after the if, the most interesting and important thing is recalculate the mid and then go back to while. So mid calculated now will be left plus right, which is 1 plus 1 upon 2. That's 2 upon 2, which is 1. So here I am updating mid in the diagram. Now left is 1, right is 1, and mid is also 1, isn't it? Mid is 1. So now let's go back to while and recheck the condition. The first condition, interestingly, observe the first condition in the while loop. We have asked, is left less than or equal to right? Isn't it? Equal to operator is there. So here you see 1 is yes, less than or equal to 1. So left has still not crossed over the right. Left has not become greater than right. Then this is still valid and we can continue the while. But the second condition you watch, the second condition is A of mid. Look at the mid in the diagram. Midpoint is storing 8. Is it not equal to the key that we are searching? That's also 8. But they are equal, isn't it? That means we have got our value at the mid place. So the condition A of mid not equal to X becomes false and the loop breaks. Now when the loop breaks, we are at the if statement and we will inquire, why did the loop stop? Did the loop stop because left crossed over right? No, not really. Because left is still 1, I'm sorry. Left is still 1 and right is also 1. So here this greater than is false. Left is not greater than right. That means it wasn't a failure. So we will go to else and we will return mid. So it will return the place or the position where X was found. I hope you got this algorithm. Last thing is that the question on this first condition I would like to ask you is that why did we write the first condition left less than or equal to right? Instead of executing all over the algorithm again, just tell me if we were searching for a key such as, let's say, 9. We are searching a key 9, then 9 is absent. You will find out that you will repeat this while loop by changing left or right repeatedly, and there will be a stage reached when A of mid will be never equal to X. This will stay not equal, not equal, not equal always, because come on, 9 is not there. So we won't get that 9. But a stage will reach when left will become greater than right. Just check this on your own. Left will become greater than right. And then less than or equal to operator here will make the condition false and the loop will break. And when loop breaks, we will check why. Why did the loop stop? Did the loop stop because left became greater than right? Yes, it is true this time. So it's a failure. Hence, we will return -1. Now, -1 is returned by most of the algorithms, searching algorithms, if the search is unsuccessful. Now, -1 is a good sign to be returned because if -1 is returned, then the calling function would know that there is no such place. Come on, the array starts from place 0, isn't it? And then goes up to n-1. So if the calling function looks at the answer -1, then it knows -1 cannot be index of any element. Hence, -1 can be a very good indication that value is not found. All right, then. I hope you have understood every aspect of this algorithm. I would suggest all of you to take some value and rerun the algorithm on paper. I always like this dry run technique and reading the programs on paper or algorithms on paper and executing them. Okay, now let's find out the complexity of this algorithm, the time complexity. That's also not too difficult. Now, here we go. Not heavy maths involved in that again. Let us say that we have been given an array. I am not writing the values now, but we have been given an array of 8 elements from index 0 to index 7. Okay, and all of them are sorted. Now we want to know what is the complexity of binary search to search a value. Now there are two cases for searching technique. For any search, there are two cases. First one is best case. Best case is very silly, I repeat. Best case for searching is very silly because best case is the case where you were searching an element at the midpoint that you found for the first time and you got your value there. That means within the first comparison you got the value, isn't it? Then the best case for any, check my words, for any search, whether it is binary search, linear search, hash search, whatever, is always big O of 1. Well, you know from the earlier videos that big O of 1 doesn't mean that we need only one comparison always. We need constant time here. That means the time to test whether a value is found or not in the best case is always constant. It will be the same because we are going to get the value in the very first attempt, isn't it? So we have written O1. This is constant time. That means there is no point in even specifying best case. Somebody asking you what is the best case of so and so search, blah blah search, you laugh at that person because this is such a silly exam, silly question asked. Best case of searching is always going to be O1, isn't it? If you are lucky, you get the value in the first comparison. But what is the worst case? So each time, when we study a searching algorithm, we are interested in worst case. Now, worst case of binary search is O log n, of course, to the base 2. This is so simple. You just watch. Initially, let L left be 0 and let R right be 7. And we will do first comparison at the midpoint. So we are actually checking how many comparisons are done. We find out the mid and we do the comparison, isn't it? So one comparison has been done at the mid, and now we either take the left part or right part, isn't it? Depending on the value that we are searching. I mean, if a of mid is greater than x, then we will go to the left part. And if a of mid is less than x, then we will go to the right part. You know that. Now imagine that we have taken the left part. Just imagine for some time. Then what we do is we again find out the midpoint of the new left part, isn't it? And then at this new midpoint, we again find out the comparison. Is this our value? Is the value stored at this new midpoint? And imagine even that midpoint is not storing our value. Are you following? That means we have already done two comparisons. First comparison was at the very first midpoint, that is third place. And second comparison we did at the new midpoint, that is first place. And we didn't get our value. And we discovered that our value is to the left of mid, isn't it? That means we are now going to search our value. Let me change the color. We are going to now search our value to the left of the mid, isn't it? Just imagine we are going to search the value in this region. And we will again find the midpoint of this region. Come on, the midpoint is going to be at the place 0. Third time we have found out the midpoint and we discover that the value is absent even over here. And then you know that the value may be either to the left or to the right of this. Imagine that it is to the left. Then left will cross right. Are you understanding? Because hello, we have got exhausted with the values. I mean, first time we had array of 8 elements, then we had partition of 3 elements, then we had partition of only 1 element, and now we will not have any value to search. So how many comparisons were really done? When n was 8, when size of the array was 8, number of comparisons done were 3. Isn't it so? So can you find any relation between this n and 3? Yes. Number of comparisons is indeed equal to log of 8 to the base 3. In general, it is log of n to the base, base 2. I'm so sorry. I'm so sorry for this. Log of n to the base 2. Because log of 8 to the base 2 is 3. I repeat, there is no heavy mathematics involved in this. Come on, this is the definition of logarithm. What do you mean by logarithm? Is that if you are given some data has been given to you, and you repeatedly divide that data into two halves, and you either take the left half or you take the right half. Now, if you divide this into two halves, this left part again into two halves, you either take left or you take right. Imagine you take the left half again, and imagine you divide it into two halves. Now, how many times you can keep dividing this partition into two halves till you are left out with partition of single element, isn't it? When there is nothing more to search. Come on, that's going to be log of n to the base 2. These are the number of times that you can divide this array of n size into two equal halves. That is log of n to the base 2. And each time we divide the array into two halves, we do a comparison at midpoint, isn't it? So Tn is definitely going to be big O of log n to the base 2. I mean, if there were 16 elements, just imagine, then we would find out the midpoint, and then we would discover maybe that midpoint is not storing our value. Then we may take some 8 elements, maybe to the left of 16, and we will again find midpoint of these 8 elements. And we discover that value is not at that midpoint also. Then we will divide this and we will take left four more elements, either to the left or to the right. So each time we are dividing our partition into two. When four elements are left out, we will divide and again check whether it is to the left half or to the right half. That's two. Two elements will then be searched and finally only one element. So how many times did you divide this array of 16 elements in correct partitions of equal size? Number of times were 5, and 5 is exactly log of 16 to the base 2, isn't it? So proof was so easy, isn't it? By the way, best case you remember is always on, big O of n, and worst case of binary search is log of n to the base 2. Thank you very much.